Okay, so I hope this is recording. Okay, anyway, so hi everybody. Thanks for joining me today. And so what I would like to do is to give you a demonstration how to use the cluster. And I will start with a bit of a warning, is that the cluster has changed completely. So since the previous years, it doesn't work the same. I would say there are a lot of differences. And I hope that I'll be able to navigate the differences, but maybe not, so we'll see how that works. In principle, that'll be fine, but really the cluster was not ready on time, so the technicians have just managed to fix it last week. There were still some bugs that they have fixed yesterday in the afternoon. So yesterday in the afternoon when I checked, it was still buggy, but after this, I asked them to fix it, they fixed it. So we are the first, as far as I know, the first users on the new cluster. And so we'll also, that's a privilege, but that also means that it could be that we encounter some trouble. We'll see about this, but hopefully that'll be fine. So before we start with the cluster, and I hope that you have managed to log in already, I'd like to give a very quick, overview of how Linux works, and I want to convince you that you already know how this works, even if you've never used Linux before. So most of you are familiar with computers. I'm pretty sure that everybody has familiarity with the computer, what is called the desktop. So for example, you can see my very messy desktop here. There are these folders, for example, other, and I can double click on it, and so that opens other. And everybody's got some familiarity with it. That what we mean by go into a folder, we don't really mean that you go into a folder. We just mean you double click on it, you open it, and you make it active. Okay. And you also have some familiarity with copy pasting documents and moving documents within that hierarchy. So these are things that everybody's familiar with. And what's nice with the Mac environment is that this is a dual environment. So here what I just did is that I created what is called a terminal. And that terminal here is a way for me that I can just type things here, and that interacts with the computer in the way that I can also interact with the mouse here. So, for example, okay, let's make something really quick. I'm going to create here something on my home that I'm going to call, for example, biod25. Okay, so you see, where did it go? biod25. You see here, I have created in my home a directory which is called biod25. I just did it right now. And now this is here the version on my terminal. And if I do ls, that stands for list, I see a list of everything which is in my home. And you can see that there is this one file or directory, it's not clear which it is, that's called biod25. So that's the one that I just created now. And the reason why I wanted to demonstrate it this way is the fact that this that you can see here, it's not another system, it is the same system. It's just a different view on exactly what is happening here. So you are familiar with that representation where you have icons, you have the mouse, you can drag and drop, etc. But there's another way of interacting with exactly the same thing, which is through this terminal, which is here. So let's open biod25. Okay, so there's nothing in it, I just created it. So the equivalent of opening a directory or going into the directory is the command that is called cd for change directory. So very small command so far, 2 letters, cd biod25. And if I press enter, you can see that the only thing that changes is that it shows biod25 at the bottom here. If I do ls, it will list the content of the directory. And what am I going to see then? Nothing, and there's nothing. So ls just doesn't do anything at all. Well, fortunately, I can actually create things. So I can do, for example, touch file.text. And I haven't pressed enter just yet, but just, to make you realize what's going on. But when I press enter here, it has appeared instantly here as well. Okay, so when I touch means create a file with nothing in it. That's an empty file. That is called file.text. And the point is really to emphasize that the terminal is not another system. This is exactly the same system. That's just a different view on what already exists there. So the command touch, for instance, you don't need to know this one. It's not very useful. But what it does is that it creates a file. What I can do as well is to copy a file. I can do cp for copy. So this one is useful. A file.text, and then I say other underscore file.text, and that creates a copy instantly of this other file. Okay, so first thing is that I can use ls to list the content of the directory. I can use cd to go into, or to open if you want, a directory. I can use cp to make copies of files. And one other thing that I like to show is I can move things around. Okay, so what I can do, for instance, I can, with my mouse, I can move things here in the previous directory, which is my home. Okay, so I just drop it here, it's in my home. So how can I reverse this? I can then do cd to my home, or cd to the previous level of the directory. So that arrow here, the equivalent with Linux is ... Okay, so that means the parent of where you are right now. The parent of biod25 is home. So cd ... You can see that biod25 has now disappeared from here. So I'm home. And if I do ls, somewhere in there, there will be this file which is called other directory. Okay, other file, sorry. You can see it's here. Now it's in my home. So again, remember there's this constant duality between the representation with a mouse and the icons here, and also the representation with the terminal. It's the same fundamental object, but I'm having two different views on the same object. These are not two different objects. There's only one object. Okay? And if I want to move this back to biod25, I'll say mv for move, other file, and then biod25. And so that here moves it back to biod25. So if I now double click on biod25, you can see that this is back here. Okay, and if I now go into biod25 again with cd biod25 and I do ls, I can see both files. Okay, so just to recap, we have seen cd, we'll use that a lot, that's to change directory, so that means open the directory. And so that can be either with the name of the directory to go into this directory, or ... to say go to the parent, I go one previous level into it. We also have seen ls, to list the content of a directory, and that's the same as just double clicking on the directory and then seeing what's inside, just watching. Okay, we have seen cp, to copy a particular file from one location to another, and we have seen mv, to move one particular file from a particular place to another. All right, so you just need to remember these four elemental operations for now. You'll be using them a lot. And for the rest, yeah, there's going to be a lot of things on screen, etc. It's going to be looking like very nerdy and stuff. But what I want to hammer in really is that you already know how this works. The only thing is that this is exactly the same as your laptop, except that you don't have access to the mouse and the icons. Okay, like imagine that you really remove it, like this is, this is broken. Well, you still have the terminal to do exactly what you're used to doing, but with the terminal instead of the mouse and the pointer. All right, I hope that this will kind of help you, remove a little bit the black box of what we're going to do, and then have a little bit more of an insight to say, oh yeah, these are easy things. I'm already doing this every day on my computer, just I'm using the mouse and the icons, but we can do exactly the same with the terminal and the keyboard. Before we move on to the actual content of what we're going to do on the cluster, are there any questions or things that you'd like me to emphasize or to explain again with that? All right, if not, then let's get to business. So that here is done. We don't need this anymore. You need to be able to connect to the cluster. So I'm going to make this a little bit bigger, hoping that people in the back of the room can have a good look at it. But there's a limit to how big I can make it anyway, and that's about something like this. So I hope that you can see when you're in the back of the room. So you should have something which is similar to this in the beginning. Signet welcomes you to the Teach cluster, blah, blah, blah. So that's all, that's a welcome message. And the first thing that you can do when you arrive, typically it would look like this, more or less a blank screen. You can do pwd, that's a new command. This one, you won't really need it much, you don't need to remember it much, but it's just so that we can see and compare how different this is for every one of us. So pwd means present working directory. So where am I right now? Where am I? So you're in home, L, LCL, UOT, biology 25. So all of us are here. This is a directory that has been created for the course, for biology 25. But this here is my login. I'm number 1004. You'll need to remember that for what's coming. And this is my home. Okay, like that's my home. But your home is something else. It starts the same with this is the same for everybody. And this here is going to be different, and that's going to be your login identifier. So I think it starts with 1004, and then there's someone who's 1005, 6, 7, etc. until 41, 46, I can't remember exactly. Okay, so if I do cd ... where am I going to go? I'm going to go to that particular place here. Okay, you can see that the slash symbol here is equivalent to, this is a new directory, the same as when you double click on something. So that'd be, you know, the top here would be the slash, then that'd be home. You double click on home, you go into L. That's a strange name, but that's the way it is. Double click on L, and then you have something that's called LCL UOT biology 25. When you double click on biology 25, well, this is where we're going to be. So if I do cd ... okay, you can see that now the little squiggly line, the tilde, has been replaced by LCL UOT biology 25. And if I do pwd, it tells me that indeed I am in home L, LCL, UOT biology 25. And I hope that you can follow along and do the same as me. And now if I do ls, what am I going to see? I see all that. So this is all of you. Hello, everybody, that's all of you. Okay, so these are all the logins that you have. You can see that they're indicated in blue here. And each of you is the owner of one of these places, one of these homes here. I am 1004, that's me here. And you, well, don't tell who you are, you don't have to, but just know that I am LCL, blah, 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 1004. You'll need this for later. And every one of you has got one of these homes here, and you'll be working within your home. We're not going to be sharing much things between each other because you have access only to your home and nothing else. Well, there's just one exception with this. So I'm going to show which with the command ls-l. So if you do ls-l, which means list long, then you see the same information, but represented in a long way. Surprise, surprise. And so what is the difference? We can see that everything is, again, sorted alphabetically here. All of us are here from 1004, that's me, to 1045, which is the last person, like the person with the highest number in the class. And you can see, sorry, that here on the left, there's this little code that's kind of different for me compared to everybody else. I won't explain what that is, even though that's quite interesting. We don't have a lot of time for this. What I will say is this. I have changed the permissions on my home so that my home is public. So I made it public. You can read my home, the content of my home. You cannot change my home, but you can read the content of my home, but you cannot see the content of anyone else's. These minus signs here, that means that, for example, whoever is number 1005, this person has access to their own stuff, but that represents the fact that this is locked for everyone else. Nobody can see what 1005 is doing. Okay, but everybody can see what I'm doing, and everybody can copy things from my home to their home. So you don't need to worry about other nasty students in the class stealing your stuff. They cannot. There are permissions that have been removed, so they cannot see what you're doing. Don't worry about this. But what you can do is you can still see what I'm doing, and you can copy things from me. And the fact that you can do this from me does not mean that you can do it from everyone else. I had to change the permissions here in my home so that you can do that. So when you do ls now in your home, So if you were in that particular place, there's always a way to teleport home, just like in the Wizard of Oz. If you do CD, bang, that brings you home. And the symbol for home is this little tilde. So when you see this, it means you're safe, you're home. But your home, remember, is not the same for all of us. We each have one of these places that we call home. And if I do ls, there's a lot of stuff in my home, but there's nothing in yours. Okay, so of course it's because I have prepared the class. I have put the content that we'll need for today's class, and I put this in my home, but you don't have it. So the first thing that you need to do is to start by copying the data from my home to your home. And you can do this because I gave you permission. I give permission to everybody to copy things from my home. There's nothing confidential here. But once it's in your home, other people cannot see it. Like this is private. So, which is the command that we'll use to copy things from me? That's cp. Okay, so you start with cp, and then you need to get the content from my home to yours. And so the first thing you need to do is to get the path of my home. So where is it? Well, you have two ways to do it. We'll do it the, let's say the short way. So // so // remember, it means like biology25. That's kind of the parent directory of your home, that's the one that's called LCL-UOT biology25. And then you need to type the name of my home. And the point is that if you do just L and then tab, bang, you can see that it looks like I'm typing super fast. I'm not able to type that fast, but Linux is quite friendly. If you type tab, it autocompletes with as many characters as it can. It says, anyway, everything starts with LCL, UOT, biology25, S10, and then you gotta, find what you need, because it doesn't need how to continue. It doesn't know how to continue. So that's, remember, I'm 1004. So you then type 1004. Then you say /*. Star means everything. Let's take it all. It's going to be good fun. And that's it. So that means copy everything from the teacher's home here, and then a space, and then a dot. Okay, that dot here that you can see here that I'm highlighting with my mouse is essential. You cannot copy things without this dot. What does it mean, the dot? The dot means here. Okay. Another way, you could say tilde, which means home. It's the same because right now you must be home. So both of them would be equivalent. So you do this, cp everything from the teacher's home to where I am right now. And then if you press enter, in principle, it's gonna work. If I do it, it's not gonna work because I cannot copy things from my home to my home. All right, so I can press enter, but that's going to be mostly confusing. So I would like some of you, or all of you actually, to run this command here. And if you run exactly that, no need to change anything with your home number or something like this, or you log in particular, that should work. Okay, cp, and then that's the path to my home here. The dot, remember, is like the parent directory, which represents the entire course, biology25. This is my home. The star means everything in my home, and the dot means here. But here for you means your home. So you should copy everything in your home if you do this. All right, I hope that some of you managed to make it work. Did anyone succeed at this? I mean, when Linux does not complain, it means all good. If it complains, it's going to be red and saying error, or something like this, angry characters, all that stuff. So I see that some people have managed. Awesome. Now, once you've done this, if you say ls, you should see the same content as my home. So you have everything that you need for today's class, for the midterm, and for the class that we'll do after the midterm. Okay? So we can also practice a little bit our list skills. Remember, ls minus l, what does it do? Represents the same information, but represents it in a long way. And so you can see the permissions that are here. Okay, the permissions that are here are whatever it is. Does anybody see the content of the of this in their home or not? Yeah, it's in your home? Okay. Good. So I hope this worked. If not, then if some of you are stuck with this, I hope that I can rapidly help them do this. So we have different files that are here. And what we're going to do is, first we're going to work with Salmon. We're going to index a genome, a transcriptome, sorry, and we're going to quantify some reads that we need to be able to analyze. And so the first thing we're going to do is we're going to revisit the formats that we've seen in one of the lectures before. So you have multiple files that are listed here. And for example, you can see that some of them finish with .fasta, and some of them finish with .fastq. And for now, well, some others finish with slurm. We'll see this in a second. So let's start with the ones that start with FASTA. And the one that we're going to watch first is this one here, the dmail old transcript or 636 fasta.gz. We're going to use the command which is called less, L-E-S-S, so it's not less ls, it's L-E-S-S, like more, the opposite of less. And then you can open that file here by typing dmail or dm and then tab, and then a tab, and then t and tab. Okay, so you can practice typing super fast with Linux by using the tab command all the time to teleport to as far as you can. Otherwise, of course, you can type the entire name manually, but it always works faster if you use the tab command all the time. Okay, so we're going to open that file here and see what's inside. And so I'm just showing this on screen a few more moments so that everybody can see which file we're about to open. And if I press enter, you should see something like this. I hope you do on your screen. So that's a FASTA file. Remember, the FASTA file is the easy one. It has this character here that means that this is a comment, like that line that's here is the name of the particular sequence, but that's not DNA. And after that, you just have DNA that's coming like this. Okay, so very simple. You have the name of something and then the DNA. So what's FBTR 0070000? That's a fly-based transcript. So that's a transcript from Drosophila. And here's the sequence of the transcript. This is something that's called less. That's a text viewer. And I can use the arrows like top, like up and down. And if I press down, you can see that I'm actually scrolling down the sequence. And of course, it doesn't make a lot of sense for my brain to just see this. I see there's text, GATC, and then at some point we see another header and another sequence, and so on. So this is a long file that just contains all the transcripts of Drosophila and their DNA sequence. Of course, the transcripts, remember, they're RNA, but once they have been reverse complemented, you can write them in DNA form. And that corresponds to the way they would look in the genome after you remove the introns. Okay, so that's all beautiful and nice, but now we're stuck in less, so how do we get out of it? It's the key Q. Just, the Q, you press Q, and at the second you press Q, bam, you go back to this screen here. All right, so if you're stuck in less here, less is really useful to see the documents, but if you're stuck in less, well, remember you just press Q, and then you go back to where you are. All right, so that was it. It was nice to see that we have this FASTA file that we understand how this works. So the first thing we're going to do is we are going to use Salmon to index the transcriptome. Remember that we have seen that we have this trade-off where you can make things run faster if you index them. If you spend a lot of time and compute resources at the indexing time, you can create a big index that'll make everything run faster. Or if you have a small index, then things will be slower. But over the course of the years, we also have seen that people have managed to do both, to make a small index that is equivalent to a big index, and then makes things faster with a small index. And we have seen that Salmon is kind of the end point of a very long optimization process, and it's got a completely crazy speed compared to other algorithms. So the way that we're going to do this is we're going to use Salmon. And so if you have a Linux at home, or if you use your Mac, when you want to use an application like less, you just have to do it. So in principle, you should be able to do Salmon like this, but this doesn't work. Okay, so on the cluster, so this is something that's very specific of the cluster. When you say Salmon, it says, please select a module to run Salmon. And then you have 1, 2, 3, 4, 5 here. And so we don't know what to do. So it says, make a selection, 1 to 5, Q aborts. Well, I want to abort. I'm going to press Q and press Enter, because what I want is to use Salmon. So important, really important now, when working on the cluster, you don't have access to Salmon and to BWA or anything interesting. You just have access to CD, LS, and less. If you want to work with Salmon or BWA, you first need to module load them. And that's something that is specific to the cluster. If you ask me, I don't know why, actually. I don't know why this is this way. I never took the time to actually investigate why specifically when you work on the cluster, you have to load the applications before you can use them, but that's the way it is. And worse is that you can see that there are the parents here. So you have to load the parents before you load the module you're interested in. So the way you do this is that you say module load, and then take all the parents. It's a bit tedious to put them all here, and then you press enter. And that takes a few moments, and it doesn't complain. So module load stdn/2023 gcc/12.3 openMPI/415. And then you can say module load, and then the one you're interested in, which is Salmon 1.10.2. This is the version here, 1.10.2, so we want the latest. And then press enter. Okay, so there's a bit of typing here for those who have, if you have a Mac, you can still use Command C and Command V to copy paste. But if you have a Windows, I don't think that works. I can't remember exactly if it does or not. So there's a bit of typing to load these modules here. All right, I hope that everybody can more or less get to that point. And if you now say Salmon, now it works. Okay, just say Salmon version 1.10.2. Yay, that's the one that we wanted to install. And it says Salmon usage. Well, that's the way it works. The commands are index, quant, alvin, swim, quant merge, etc. So at least it doesn't say something that doesn't make sense. It says, yes, Salmon is this version. Just tell me what you want to do with it. So that works. So now, what we'd like to do is to index the transcriptome of Drosophila. So how do we do this? Well, the command would be Salmon, quant, etc. But never do that. Okay, just don't do that. So why is that? Because here you're on a computer cluster. You're not on your own computer. It says teach login 01. Maybe some of you have login 02. I'm not sure. Login 01 means it's a login node. You're not supposed to do any work on this, and you're just supposed to do CD, LS, load the module, but do practically nothing. If you do things that are actually computationally intensive, what's going to happen is they're going to kick you out. Not of the university or something like this. It's just that you'll be unlogged, and then you'll have to relog because your job is going to be canceled. That's not the way this works. So the way it works is that you have to do something else, and it's not very good teaching practice, but I'll make you do it now, and then I'll explain how this works. So the command you have to do is there is this script here, which is called Salmon index.strum. You have to do s batch Salmon index.strum, and then you press enter. And it should tell you job, submitted batch job, something here. So we should have a job 120, 21, etc. Okay, so that's s batch, and then you have copied in your home salmon index.slurm. So when you do this, it should work. And if I do SQ, oh wow, that's amazing. SQ is everybody who is actually who has submitted the job, and you can see that there is approximately 12 or 15 students at that point who have submitted the job. So I'm job 119, but this goes until 133. The SQ here shows all your jobs here. Our logins are so long that we can't even see the entire string here. So we have to guess who's who. I know I was first. So when my job is finished, then it means that my indexing will be finished, and those who launched it just a few moments after me will finish a few moments after me. So while this is running, let me explain to you a few things about what's happening. So here, this is the way that you work on a computer cluster. This one's called SciNet. The Teach cluster is on SciNet. So your computer is the one where you're typing right now. It doesn't look like this, but if you're working from home, it would look like a tower like this. When you use SSH, what happens is that you connect to what is called a login node. This one is written as teach01. It's no longer called this, it's called teach login 01. So that's a relatively weak computer. It does not allow you to do a lot of work. And if you try to do a lot of work, like I said, you're going to be killed. What you have to do instead is to say, I want to schedule a job using Slurm. Slurm is just a scheduler that takes your job and then distributes it to another series of computers which you never access. But these are the workhorse. These are the ones that actually do the job of what we need to do. And Salmon, well, it's not crazy amount of computations, but still, you need a bit of computation. So you're not allowed to run it on Teach 01. You have to use Slurm to delegate it to other computers that will be able to run this on one of these computers in the background that are here. And these are really powerful. You have a lot of compute power there. And so that can take care of all our indexing together. But if we do this on Teach and we all work together, we're going to block that node or that computer. It's the same thing. And then we're going to be kicked out. So never do anything that's computationally intensive on Teach 01 or Teach login 01. You always use Slurm to delegate to the computers that actually do the work. Okay, so these are called compute nodes. They're here, and this is your login node, so you never do anything on the login node. This is not relevant because that has changed on the new cluster. So what just happened when you do sbatch with Salmon index Slurm is that this sbatch, it should be called Slurm, I guess, but it's not. The S stands for Slurm, so that's a Slurm batch, where you say, I have written here a little command, a little program. So run that program in the background on the compute nodes, the one that are actually powerful. Okay, so let's see how we're doing with the computations. Oh, that's nice. Almost everything is finished. So we see that there were something like 22 or 24 jobs have been started. That's wonderful. Let's inspect the content of this Salmon index.slurm. Salmon index.slurm. I use less here, which is my text editor. And you can see it's got this a file that looks like this, like blah, 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 like really weird stuff like the shebang is called bin bash, sbatch, whatever. But then we see some things that we are familiar with here. Okay, module load, standard amp, etc., and module load Salmon. Okay, so we've seen that you need to module load in order to have access to Salmon, otherwise you can't use it. And then comes the actual command that matters, is the one that says Salmon index. So we're creating the index of the entire transcriptome, and then you just have to know how to use Salmon. That's the way you use it. Minus T for the transcriptome, and minus I for the index that is created. Okay, that's minus I dmail Salmon index. That's going to create something that's called dmail Salmon index. So let's press Q to go out of less. And if I do now ls minus L, oh wow, that's so cool. Dmail Salmon index created on February 12th at 2:46. That's just a few moments ago. Okay, so that has worked. That has created my index of the transcriptome of Drosophila. Okay, and that's Salmon is not the name of the species, that's the name of the tool, of course. All right, so what's next? Of course, we want to quantify the transcripts of one particular experiment. So there is this summon quant script here. So I let you guess how we're going to submit that script. I'm going to wait just a few moments, but you go ahead and start typing. I'll try to guess exactly how I would submit that particular job here on Slurm, on the workhorses. That's of course sbatch, and then the name of the file, so salmon quant.slurm. So I'm job 144, and if I say SQ, just wait a few moments so that some of you can maybe have time to run this job here. I see that, yeah, many of you have managed to start running the job. That's relatively fast. So you see the creation of the index was maybe 2 minutes, something like this. It was quite fast. And this job here, once the index is created, it's taking some transcript data, and then it's quantifying them in the transcriptome of Drosophila. So let's see if, actually, it was done really fast, because you see, I did SQ, and by the time I did SQ, 144 was not even, oh, there it is. I'm saying nonsense. So let's see, everything is finished. So all the jobs have run. I hope that they're all successful. So you see, it's just maybe 1 or 2 minutes as well, really fast. And that has created something that's called dmail RNA-seq quant. So let's have a look at what we just did at this salmon quant.slurm. We say less salmon quant.slurm, and we can see that again, the job starts with module load. So of course we need this. Remember that you cannot use salmon if you don't module load first. And then it uses that kind of magic incantation here. Salmon quant minus I means, quant means quantification, of course. I is the index. It says take the index from dmail salmon index. Minus LA is quite interesting. It means the library type is automatic. You just like guess everything for me. I'm not in a mood for telling you what's happening here. You will just guess it. And we see that there is this minus R, dmail RNA-seq.fastq.gz. That's quite interesting. It means the RNA you're reading from is from dmail RNA-seq.fastq.gz. That's one of the files that you have copied. So that's something which is an RNA-seq experiment in the FASTQ format. We'll see this in a second. And minus O means output. The output should be in the directory called dmail RNA-seq quant, the one that has been created recently. Okay, so basically all this is done for you. These scripts already exist. You just have to copy them and then run them. But you can see that in principle that runs fine for you. I press Q to exit this. And let's have a look at the FASTQ file. That was this one here, dmail RNA-seq fastq.gz. So I do less dmail RNA-seq fastq.gz. So you see how I use less all the time. This is just a text viewer, pretty useful. Leaving this on screen a few more moments. Dmail RNA-seq fastq.gz. And if I press enter, I've got here a typical FASTQ file. So remember FASTQ file? This is what comes out of the sequencer. Like you really run your experiments, do some biology, prepare a library, put the library into the sequencer, and then the sequencer outputs a FASTQ file. So that's really what has been sequenced. That was an RNA-seq experiment, meaning that this is in DNA form. But remember, this is because there was a reverse transcription. It used to be an RNA. So this is some piece of an RNA from Drosophila. And remember as well that in the FASTQ format, every read is represented over 4 lines. That the first one here is the name of the read. The second one is the sequence that was decoded. The third one is always a plus. And the next one is the quality, the thread quality. So this kind of weird code here tells you how confident the machine is about the fact that the nucleotides are really the ones that are claimed here. And remember, like letters like F, H, G, they're actually high confidence, but weird symbols like question mark, equal, etc. means low confidence. So these nucleotides kind of low confidence. But these ones that correspond to FFF, HG, etc., they're high confidence, for instance. So that's one read. Then there's another read, which is here, then another read, which is here. Each of them is taking 4 lines of this file here. Okay? So we see that really the FASTQ format that we have studied together, it actually works like this. This is a real experiment, by the way. This is not something that I invented or typed myself. This is really something I got from the internet. So I press Q to go out, and now we have created this DMail, this one, DMail RNA-seq quant. So it's in blue, meaning it's a directory, so I can go into it. I say cd DMail RNA-seq quant. I press enter, and then I do ls immediately to see what's inside. And I can see that there's a file which is called quant.sf. That's the one that contains the quantification. Right, cd into the DMail RNA-seq quant, and then ls, you will see the quant.sf, and I can see what's inside, as again, always with less, quant.sf. So I press enter, and I see that that's a table with name, length, effective length, TPM, num reads. Name is FBTR 007, etc. Remember, that's the first transcript that was in our file. This is a transcript that has length 3,537 nucleotides. Effective length, you don't need to worry about this. This is a correction that Salmon makes to kind of equalize some biases in the genome that are known. And next, you can see TPM and num reads. What is TPM? Anyone can guess what TPM is here in this context? It's the transcripts per million. That's the unit of expression that we have studied in one of the classes before. So this one's easy, it's 0, which means that there was not a single read that has been discovered for that particular transcript. So the number of reads is the last column, so that's 0 as well. They don't align very well because of the tab. Okay? Like effective length is pretty long, so that makes everything a bit shifted. That's annoying. So num reads corresponds to that 0 here. The first transcript that has some expression is this one. You can see that it has a TPM of 254. You must have it in your result as well. And it has 3 reads. So there were only 3 reads that were associated with this particular transcript, and that makes a TPM of 254. So TPM is really the unit that we care about for the expression of the transcripts. As usual with less, I can scroll down with the arrows, like the down arrow, and then I see there are many transcripts that correspond to many genes, and they have many reads that are expressed that correspond to their expression. So I can scroll down for a long, long time. There's really a lot of them, and there's not a lot that I can learn by just scrolling down, but just to show you, yeah, a lot has happened really fast in the background, thanks to these super powerful tools like Salmon. First, we index the transcriptome, and second, we quantify an experiment, and that tells us, okay, that gene, whatever it is here, is expressed at that level, 254.12. How could I know what this gene is, what it does, FBT? Or anyone remembers or has an idea of one thing I could do to get an idea what is this gene, what it does? I can go on the internet, I can actually Google it, I can try that, and it will actually work most of the time, but I can go to Flybase. Flybase is the database of the fly genome, and if I go to Flybase and input that particular code into Flybase, it would tell me what I need to know about that gene. I would maybe then click left and right to get an idea. You can try your luck with ChatGPT. I'd be surprised if it knows really all the names of all the transcripts of Drosophila, but maybe it does, I don't know. So most useful is to go to Flybase and see what is this gene, what does it do, is it anything important or something like this. Okay, so that would give me an idea of, okay, why is this gene expressed? Is it an important gene or maybe not? I don't know. And when this is done, I press Q and I go out, and I'm now in the dmail RNA-seq quant. And to go home, I can either do cd ... or teleport home, like Wizard of Oz style. CD just brings me home. And I can see this with the wiggly line, the tilde symbol here. All right, so ls minus L to see what we've accomplished. We have created the dmail Salmon index, and we have created the dmail RNA-seq quant that corresponds to the quantification of the transcriptome of that experiment here. That was this dmail RNA-seq FASTQ.gz. Okay? All right, are there any questions before we make a short break? So the question is, what's the Spades 3.15? So it's for genome assembly, and that's something that we won't worry about today at all, and we won't worry about this until next class.
Should we have it in that?
No, because you don't have it, right? Yeah. It's an issue of permission. I made a mistake with the permission. I meant to allow you to have it, but you don't have it because of permissions. You will have it when you need it. Don't worry about this. Are there any other questions before we make a short break? Okay, so let's take 5. It's 3:01 on my watch, so we start again at 3:07. So have a short break. Okay, so welcome back. One question that just came up 2 times. So of course it's very scary that you're supposed to have one question about genome assembly in the midterm, etc. So don't you worry. What's going to happen is that I'm going to remove the third part from the midterm because we haven't seen yet what you need. So the midterm will be just the first 2 parts, the ones that are about the transcriptome and mapping the reads. The part about genome assembly will not be part of the midterm. Okay? So I'm just going to slash the midterm, but instead what it's going to be is going to be one extra exercise that will be at least 2 weeks after. So we will do it, and it will be just another couple of points that you can get from these exercises. But I'm just going to split the midterm in 2, and the midterm proper will have only the part 1 and part 2. So don't freak out because you see Spades, because you're supposed to do something with genome assembly. I'm aware that you haven't seen anything about this, so I won't ask you to do this at the midterm. I haven't had the chance yet to modify the midterm, but don't worry about this. As soon as I can, I will modify the midterm and leave only the first 2 parts. The third part, it will be after we have seen the class on how to assemble genomes. So don't worry about this. So did any questions come up while you were on the break and that you'd like me to re-explain or go deeper into about the first part? As a quick recap, we have learned how to navigate through the system with CD, ls, cp to copy, mv to move, etc. We also have seen that this is exactly the same thing as what you're used to doing with your own desktop, like this virtual desktop, except that you replace the click and move with the mouse with the commands at the keyboard. But it's exactly the same. It's one and the same object. We have also seen that we can use Salmon to quantify the transcriptome, but that we don't do this directly by calling Salmon into the login node. We need to use a system that's called Slurm, where we delegate the computations to another couple of computers. And that's the command sbatch here. So in the second half, now we're going to see how to use BWA. BWA, remember, that's a software to map reads. So that's something that you take DNA reads and they're mapped into a genome. Salmon was quantifying the transcriptome. So that means that it's not really mapping the reads, it's just counting how many transcripts were produced in each condition. So we have here the Drosophila genome, which is called dmail all chromosome or 636 fast-status. So let's have a look at the Drosophila genome here. The way to look at things, as usual, is less dmel, all chromosome, etc. And then when I press enter, I go into the genome of Drosophila. So we can see that there is this usual FASTA symbol here. Okay, that's a FASTA file. 2L is the name of the chromosome, and then this is a couple of information about the chromosome here, like log 2L1 to 23 million, etc. That's the length of the chromosome. Some other things that I may be interested in, for example, the release 636 and the species D male. So D male, that's Drosophila melanogaster, and the release 636. This just means that there were at least 6 versions of the Drosophila genome before this happened. And so this is just like the 6th big version of the Drosophila genome and the 36th sub-release of that particular sequence. So this is already an old version of the genome. By now, it must be much more than 636. That keeps evolving over time. Flybase releases a genome approximately once per month, something like this. So that's about 12 releases per year. And then here we go. You have the sequence of the chromosome, 2L, etc. So if you scroll down, this will go on and on and on and on and on. That's an entire chromosome. So these are millions of nucleotides next to each other. Okay, so that's just the reference genome of Drosophila, and that's what we have here. So what we'd like to do is to use BWA to index the genome and then map some reads that I've prepared, which are called a genomic 1 and genomic 2 that are here. So let's use BWA, and if you type BWA, of course it does not work. Oh, well, no, it doesn't work. Because, why is that? Well, we need to load BWA before we can use it. Okay, so as usual, it does not work. So Q to abort. I think in this case, if I do module load BWA, I think it works. Okay, we don't need to specifically load STD and 2023. I'm not sure why. Maybe this thing is already loaded because that's the standard environment, like CDLS or whatever that is. I'm not too sure. That thing did not exist in the previous version of the cluster, so I'm not yet familiar with that. So if I do module load BWA and I say BWA, it seems to work. Okay, that at least prints something meaningful here. So I tapped BWA and then it says program, BWA alignment with Barrows Wheeler transformation. Yes, that's the one. It says 0718 dirty. Don't worry, it's got nothing dirty in it. So that's the version here, the most recent. So that's the one that we want. And here I have a couple of commands that you can use: BWA index, BWA mem, etc. Okay, so basically we know how to load BWA. So that's module load BWA, and then we will do BWA index. So why do I not do BWA index, dmel, all chromosome? What's wrong with doing that? Is that we do not do anything on the login, on the teach login nodes. Okay, this is your login node. You do not work on this node. This node is just for you to submit a job using Slurm to the real workhorses which are in the background. So you never do that. That's what we'd like to do, of course. That'd be nice, but that's what you're not allowed to do. The login node is a not so powerful computer. You can do a bit, but not that much. And if you insist, then yeah, you may be cut out. So we need to do something of the form, sbatch, and then blah, 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 something like this. So let's have a look. Where did the teacher prepare the work to do BWA? Oh no, the teacher did not prepare the work to do BWA. Oh, what a terrible person. We need to prepare it ourselves. So, okay, we need to write now our first Slurm job. It was easy in the first half. We just had to submit something that exists, but now we have to write it. So that's where things become a little bit more complicated. So whenever you create something new, my advice is don't create something new. It's take something that works and edit it, but don't start from scratch. So we're going to apply this principle, and the first thing we're going to do is to copy Solomon index into a new file that we call BWA index. We're not going to actually create something from scratch. So the command for this is cp Solomon index. Okay, and then we need to give a new name for the file, so that'll be bwa underscore index dot slurm. So now we have two files that are identical, Solomon index and bwa index, and I'm going to edit bwa index to be able to index with bwa instead of with Solomon. Okay, so I need to know the name of the genome here that I want to index. Is that female chromosome or 6, etc., so that I can run this into my my code here. So when I do less bwa, I can see the code. It's this one. It's exactly the same as the previous one. It still has Solomon, but I want to replace this. And you see the problem is that less is just something to view. It doesn't allow me to do any edits. It's just a viewer. So I cannot use less to make any modification to that file. It's not going to work. I need to go out, pressing Q, and I need to use a text editor. Less is not a text editor. This is just a viewer. So we need a text editor. And the text editor, which is the least painful to use in Linux, is called Nano, because it's a small text editor. So you do nano bwa index.slurm. So that's the name of the text editor here, nano. Okay, and then you press enter. And you see this kind of, old-fashioned way that computers used to look. So I'm actually old enough that when I was a child, computers actually looked like that. So I remember when things were looking like this. For you, it's probably only when you see a documentary or a movie from the 70s or the 80s. But for me, it's like, oh yeah, I remember. Those were the days. Well, so now we need to edit this file so that it does what we want. So you can use the arrows to move around here. You can see like this little square that moves. And I can use it, again, to delete stuff with the delete command key. Okay, I'm just pressing the delete key and I'm removing this line entirely. Up, okay. Module load Solomon. No, that's not what I want. I want module load BWA. Okay. All right, so I don't care about Solomon. I want BWA. And this Solomon index, it should be BWA index. And then the rest is the name of the genome. So you see that's much easier to actually work with a file that already works and edit it instead of create something from scratch. So no T. In this case, it's just that. Okay, it's a small file, but that's already a great beginning the first time you do it. So your file should contain module load BWA. Remember, you always need to do this, otherwise the computers cannot even use the software you want. And then it's BWA index, no T. It's a different way of using the command compared to Solomon. So that's BWA index, and then the name of the genome you want to index, not the transcriptome. So DML all chromosome R6 36 fastat.gz. Okay, so I hope that everybody can get there. If you're typing this thing here, there is only a 3% chance that you type this without making a typo, of course. So maybe that's going to cause trouble. So if you have anything that does not work when we run this slurm script, most likely it's because there's a typo in this impossibly long chain here. Okay? All right, so how do we get out of here now? Well, what's really nice is that Nano gives us some hint of what to do next. This little, character here is actually control. That's the control key. So that means Control G is help, Control X is exit, Control O is write out, etc. So we just say Control X for exit. And then what has happened is it says here, save modified buffer. So what are you saying? Buffer, where's the buffer? I don't need any buffer, I don't have any buffer. Well, yeah, that's just the way computers spoke back then. The buffer is what you see on screen. That's the buffer for some reason. So do you want to save basically what's on screen? Well, hell yeah. And so you can see that if you press Y, it's going to say yes. And if you press no, then it's going to just exit without saving your work. So you want to press Y, not N. And Control C here, you're going to cancel the exit process. So I press Y, and when I press Y, I'm still not done. It says file name to write, bwindex.slurm. And so here it just asks how I want to write the file. So if I just press enter, it's going to overwrite the file, but I can give another name if I want. So in principle here, if I press enter, finally I'm out of Nano, and my job has been saved, I hope. So I can add check and can use less, BWA index, and I can see that, okay, it's fine. Module load BWA index, email, that's good. Q to get out. Now, how can I submit that job to the compute nodes? Always the same thing. It's sbatch BWA index learn. So I'm job 167. And so we'll see exactly how things run. So SQ. Wow, plenty of jobs are running. So to index the Drosophila genome, it's what, 4 or 5 minutes, something like this, approximately. So I let you make progress with this if you're still trying to do it. So I hope that everybody has done the nano bit here and replaced Solomon with BWA and has pasted or typed the name of the Drosophila genome. No, if you just do BW index from, nothing's going to happen. This is a text file. It's just going to say, I don't know what you mean. I don't know what you want from me. So sbatch says, I've just given you a small recipe of what I would like to do, but don't run it on teach login 01. Run it on the compute nodes in the background. So you have to anyway, because if you try to run this on teach 01, teach login 01, you may be kicked out. They may say, no, you're just trying to do something that's fishy here. We told you, don't do any operation on teach login 01. This is not your computer. That's not the normal architecture. This is a cluster, a computer cluster. So I think that's a good transition to, while this finishes, to explain a few things here about the architecture of the cluster. So that's here the global, let's say, workflow of what you do. Your computer use SSH to connect to teach01 or teach login 01, and then use Slurm to work on these computers which are here in the background. So you have seen that in the scripts we have this sbatch time equals 400. So the point is that by default, so you have the right to use 4 hours of compute in a row on the teach cluster. This is the generosity of the university for the students. Any job that you are interested in, you're given up to 4 hours, but by default, it's 15 minutes. So it's going to cut you in 15 minutes if it's not done. So you can request 4 hours, but if you do not, you have by default requested 15 minutes. And so that's a bit annoying in the sense that some of the jobs are kind of close to 15 minutes to run. So if your job is not finished when the bell rings, what's going to happen is that you just get interrupted. Pull the plug on your job so it doesn't delete stuff, but if it was in the process of doing something, it will just not finish. And sometimes you won't even know this. You'll think it has finished, but it didn't. Imagine that this is printing something on screen or creating a file, but then this happens exactly at 15 minutes, then the file is interrupted in the middle. And that's not easy to see because the files are really big. So that's why I have requested 4 hours all the time, and I advise you to do this all the time. Anyway, if it takes 2 minutes, it's going to take 2 minutes. You're not going to block anything for 4 hours, okay? So my recommendation is always request the 4 hours, for everything and all the time, because what can happen if you run for 15 minutes and your job is not finished is that it will be cut in the middle and you may not even notice it. So always ask the maximum that you can. And most of the things are finished way before 15 minutes anyway, so there's not a huge cost with this. So this is also allowing me to kind of answer the previous question a little bit better, is that a computer cluster by definition is a shared resource. You have multiple workers, multiple people, not computer, working on this computer organization at the same time. So the Slurm is also a queuing system. That's why it's called SQ. If all the computer nodes are busy, people are, imagine you have like 100 other classes at the same time that are using the teach cluster, then we can saturate the compute nodes. They can be too busy with dealing with all the requests. So what happens then? There's a queue. You have to wait until your request is being processed. So that's what Slurm is about. It kind of makes a big queue and say, look, there is kind of a point system or a priority system, which is first come, first serve. If your number is 300 in the queue, you're going to have to wait until the first 300 people have finished their computations before you can do yours. And the point is that no matter what happens, after 4 hours, everybody's job is finished. So that's to make sure that there's a turnover. So you have 4 hours to do your stuff, but that's not your computer. This is someone else's computer. So 4 hours for you, it's for free. But after 4 hours, no matter what, this is the end. And then you'll be kicked out, and then someone else can take your place on these computers. And then you can request another 4 hours, it's okay. But that's just to make sure that there is continuously a turnover of the users, that you don't get stuck for 1 million hours because someone is computing Bitcoins on the cluster, okay? So that's the reason why things are this way. It's a system to make sure that you allocate the resources on a first come, first serve basis, or sometimes with a point system. That's why the architecture is kind of unusual. On your computer, you do what you want. On a cluster, you need to know the rules, and the rules are meant for sharing the compute resources. All right, enough about this. I think that by now, maybe this is finished. Oh yeah, everything is finished. So ls minus l, what do we have? So there are these files that are here. Actually, I think they were here before. So these are the files that have been created by BWA. I probably forgot to remove them before. I should have removed this here. That would have made the exercise much more difficult. Now you have actually everything even before you started. But these were the files that were created by BWA. You can see this. The date here is telling us that these are the recent files that have been created. So those are here the index files that have been created by BWA. And now we need to map those reads into the Drosophila genome. So again, we are going to not start from scratch, but create a file that already has some components that work. So I'm going to say cp bwa index slurm, and I'm going to create bwa underscore map dot slurm. So I'm making a copy of this index script that is here, the recipe to index the genome. And now I want to map the reads. So I'm going to copy this file name here because it's going to be quite useful. Again, if I use less, it's not going to allow me to modify the script. So I need to use nano and then bwa map slurm. And that brings me into this old-fashioned way of displaying stuff. Okay, so BWA index, etc., module load. So we still want module load BWA, of course, but we want to map the reads. We don't want to just index the the genome. So that's BWA mem. Okay, it's not BWA map, it's BWA mem, and that's the name of the algorithm here. It's called the mem algorithm. And then the name of the genome that we have just indexed, and then the name of the first file, and then the name of the second file that contain the reads. Okay, and then we say -o for output, and I'm going to call it a mapped.sam. All right, so bois-mem, BWA-mem here, that's the name of the algorithm we want to use for mapping the reads. Then the index, which is D-metal chromosome R6, etc. And then the two files that we're going to use here that contain the reads from the genome. And -o for output, mapped.sam. I hope everybody got it. If not, you can, when I'm going to close, you can guess. Okay, that's BWMM, the name of the index, the name of the two files, -o mapped.sam. So I'm going to exit now, so Control X to exit. Save modify buffer, yes. Why? File name to write bwmaps_term, that's good. Enter. Okay, so now I'm going here and I'm submitting my job. So S batch bwa map. Sorry. Submitted batch job 186. My job's here. And I see other people have got their job, so that's nice. You can see ST actually, this is the status. OR means running, and this is why the time left is 4 seconds removed from 4 hours, but PD is pending. So these are people who are on the queue. So it's not that really there's no space for them, it's more like there's 1 second of queue, something like this, for everything to start. And so they still have exactly 4 hours. They haven't used any of the compute time yet at that moment. Anyway, so that's the information that you can see here in SQ. Okay, so while this is running, let's have a look at the files that we're mapping here. So genomic1 fastq.gz. So I'm using less, and I'm opening the file genomic1, and that is a fastq file. Okay, so the name of the first read is paired and read 11. Here that's the sequence, the plus, and the quality of the sequence. Paired and read 21. Okay, so you see 1, 2, 3, 4, 5, and there's this /1. And we'll see in a second what that means. Is that if I go to the other file, the genomic2, it says paired and read 1, 2. So these ones here all have a 2. And the point is that they are paired and, which means that this sequence here pairs with the first sequence of the other file. It's the other end of the same DNA molecule. So there's one DNA molecule that has been sequenced from both ends, and that is the second half. The first half is in the first file. Okay, so these sequences are coupled. That's the most important. What's interesting as well is that the file map.sam is either created or on the way of being created. To know if it's finished or not, I need to do SQ. Okay, that's good. So you see, this is important to know that the job has completed. If the job has not completed, I can look at it, but it's not finished. It's being produced by the script. So that's why I'm always requesting 4 hours, and it takes maybe 2 minutes, but that's okay. Like, better ask everything that you can use rather than taking the risk of being interrupted in the middle. So map.sam, let's have a look at it with less. And this is a little bit of a disappointment when we look at it with less. So if you remember the SAM format, it didn't really look like this when I showed it in class. Well, actually it did, but there was not a lot of emphasis on this SQ at SQ line. So this here is the header. And what does it contain? It contains all the names of all the chromosomes that are in the genome. So sequence 2L with length 23.5 million, sequence 2R, 3L, 3R, 4X, and Y. You can see that these items are the chromosomes proper, but you also have sequence 2 SEN map scaffold 10D1684. What's a scaffold again? Remember, this is the species of contigs that are not fully assembled. So the genome of Drosophila is not completely finished, and so you have hundreds and hundreds of these scaffolds here. Some of them have got a silly name like that, and that goes on and on and on and on. Okay, so that's the problem with genomes like these. It's a very good quality genome, but like all the genomes, it's not fully finished. So you have an impossibly high number of sequences here that just show all the scaffolds that are somewhere, but we don't know where. You have only chromosome 2L, 2R, X, and 4. That's 4 chromosomes in Drosophila. And then we bothered with hundreds of lines of just like, oh yeah, and there's this scaffold, and that scaffold, and this scaffold, and that scaffold, and this one, and this one, and this one, and this one. It goes on and on forever. So, you know, I can scroll for a long time, and I'm not going to go much anywhere. So that's very annoying that because of that, the SAM format is not so useful for me. So that'd be really nice if I had access to a specialized tool to read the SAM format and remove the header for me and, you know, give me some information directly. Well, thanks God that exists. This is something that's called SAM tools. So here we go, SAM tools. Oh no, failed again. So what's the reason? Yeah, well, no, there's nothing at all by default. There's just CD, LS, nano, all these things. SAM tools, complicated, takes resources, so you don't have it. You have to do module load. Okay, so let's see if it works with module. So Q, I abort. Module load SAM tools. I don't think it should work because it has GCC 12.3, but I think we already did load GCC 12.3. So in principle, it'd be module load GCC 12.3. Oh, by the way, that's probably why it worked with BWA, because we had already loaded this with Summon. So probably in reality it should be so module load, both of them. Okay, so we have loaded them already before. So nothing bad is going to happen. And then module load SAM tools. Okay. And then when you do SAM tools, this time, yes, it works. It explains to you how to use it. Okay, so the module loads, of course, compound with each other. When you have used module load in the beginning to load Salmon, I think it had loaded GCC already and standard dev, and then that's why you could do module load BWA. I think, not too sure though, not too sure. Best is to load all the parents that you see here in blue, and then load the particular tool that you want to. Okay, so anyway, when you have SAM tools, what you should not do is SAM tools view mapped.sum. Don't do that. Okay, so I'm just showing it, but don't do that. If you press enter at that moment, you'll regret it very much. You'll regret it. I'm going to do it just because it's fun, but don't do that. Okay, so don't do that. If you can resist at that point, don't do that. So if you press enter, well, that's what's going to happen to you. Okay, like this thing, and it'll spit on and on and on. And the problem is, once you've done this, you cannot scroll up back. It was so long that it has erased everything you've done before. Okay, so well, that's nice. Now you have a lot of garbage on your screen, and you've lost access to whichever commands were before. So don't do that if you can resist. Now, what do you do instead? You say, okay, that here is going to spit out the content of the file on screen, but capture this with our favorite text viewer, which is less. So this here is called the pipe character, or the vertical line. That's something that's just usually above or next to the enter key on the right of your keyboard. Okay, so that's the vertical line here. So SAMTools view, the name of your file, pipe less. So now this is going to put this into less. And now what's nice is that with less, I can just go up and down. And if I press Q, I'm going to get out of it. So Linux is very nice because you have this pipe character. It means takes the output of one program and put it as the input of the next program. And you can do like this, multiple blocks that allows you to program very, very fast, super easily. So the header is gone, that's great, but this is kind of hard to read because the lines are fairly long. So one thing that you can do to make it a little bit more readable is to type minus here and then capital S. And when you do this, it says chop long lines, press return. When you press return, yes, and now it becomes very orderly. Okay, so that's minus capital S, and you press return. So what do we see here? We see the SAM format, which is the complicated one. Remember, there's one that's pretty more complicated. It's this one. So paradigm read one, paradigm read one. Oh yeah, of course, they have the same name because they're the same read. It's just two, not the same read, the same molecule. These are just two different ends of the same molecule. This here is the infamous code, the bit code that tells us something about the read itself. But this is more interesting, 3R, and this, what is it here, 3R? It's the chromosome where the read is mapped. And that here, what is it? Is the coordinate on that chromosome of where that read is. So you can see that this read is at this location here, which is 16 million. And the other one is, well, very close. Why is that? Well, duh, this is a short molecule. It's going to be at most 500 base pairs. So, of course, both ends have to map very close to each other. They map 300 base pairs of each other. So that shows that the molecule itself was 300 base pairs. 60. Anybody remembers what this 60 here is? It's the mapping quality. Not to be confused with the nucleotide quality, the Fred quality that you have in the FASTQ. So that here, it means that there's only one chance in a million that the read does not go here. Okay, so you can see the qualities are pretty high, 60, 60 all over the place. Let's see if we scroll down, if we can see lower quality. Oh yeah, here, 0. Quite interestingly, it says that the location is in rDNA. rDNA is the DNA that codes rRNA. So why? Can anyone guess why you have quality 0 here when you map something to the rDNA? It's because ribosomal RNA, remember, that is the most abundant RNA in the cell. How is this achieved? Well, because the transcripts are actually repeated. The ribosomal DNA, like what codes the ribosomal RNA, you have many, many, many copies of it. We're talking hundreds. To make sure that you can produce a lot of it, you have one polymerase on each of them. But this is also duplicated so that you can have a lot of throughput. But because it's duplicated, it means that you never know exactly which repeat is which. So the quality is always 0 here when it says, oh, I'm just saying it goes here, but really it could go anywhere. I just chose one of the repeats at random, but if you have 100 identical sequences, I'm saying it goes here, but it could be at any of the other ones. So that's a quality 0 here. Quality 17, it's something in between. Right? That's not 0, not 60, which means, yeah, probably goes there, but not too sure. Remember, 20 would be a 1% chance of error, so that's a bit more than 1% chance, maybe 2 or 3% chance. So what's the reason here? Either the read is low quality, doesn't align very well with the genome, or more likely, that particular place here on chromosome 3 or at that location is partly repeated. Like there are other sequences in the genome that look like this, but not exactly like that. All right, we could spend a lot of time interpreting this file here, but that's not exactly the point. The main point, I press Q to go out, is that I use SAM-tools view to be able to decode the output, the SAM format, but to not print everything on screen, I use pipe less to capture the output. Okay, and SAM-tools view nicely removes the header for me so that I don't have to read this impossible header here. So SAM-tools view does other things which are quite interesting. One of them is that it can filter a minimum quality. If I do minus Q20, okay, it means put a threshold at quality 20. Everything that has quality less than 20, don't show it to me. I don't want to know about stuff that you don't know where it goes. Okay, so minus Q20, it works just the same, and then I press minus S, minus capital S, enter. But this time if I scroll down, I will see mostly 60s, and the zeros are gone, the 17 are gone. Everything that is below 20 is completely gone. I don't know if you can see it by me scrolling down here. It just shows that the anything that is below 20 is removed. We see only the good stuff. Now 59 is still go, but anything that's like 17, 5, 3, it's removed. Why is that? Well, because very often you want to know only the good reads, the ones that are actually mapped with high confidence in the genome, not the ones that are placed at random locations because they were impossible to map. So that's one thing. You can do some selection with SAM-tools view. Another thing that you can do is you can use filtering, like minus small f16 here. It will select the reads where we have answered yes at the question 16. And the question 16, remember, that's actually question 5, is the read mapped like this or like that? So is it on the forward strand or the reverse strand? And if we do this, what's interesting is that, okay, minus capital S, enter, is that now you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let me show you the previous pattern. When we don't do this, it's, if you don't put minus F16 here, you see, of course, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. Why is that? Well, think about it. When you have a read which is a paired end read with two ends from the same molecule, one maps on the forward strand and the other maps on the reverse strand. You're sequencing from different sides here. Only one of them is on the forward strand. So that's why when you select for the forward read here by saying minus F16, what you've got is just one of the pair. You don't know which, if it's the first or the second, but this is 1, 2, 3, 4, 5, 6. So that just shows you here that all these reads, you always have one that's on the forward strand and one that's on the reverse strand. But that's normal. They're coming from different ends of the same molecule. It has to be the case. Well, that's good. We're just checking that molecular biology makes sense and that BWA is cognizant of it. That's really good. So what we can do is doing the reverse, to say the ones that are on the reverse strand, they have answered no at the question 16. So that's minus capital F16. So it's the same, 1, 2, 3, 4, 5, etc. Except that this time, you're just selecting the ones that are on the reverse strand, not on the forward strand. Okay, what are the applications? Not much at that stage. It's not super interesting. But it's still nice to see that everything's coherent and consistent. One of the reads is on the forward, the other one is on the reverse all the time. Okay, another thing that is interesting is we can count with SAM-tools view. So if you do a minus C, it means just count the stuff. Okay, so minus C map.sam, it says, well, there are 101,000 reads that have been mapped. Okay, yeah, sure, but how many are good quality? So minus C, but this time also minus Q20. And it says, oh yeah, good quality, a bit fewer. Only 93,000 of those are trustable. The rest, like these 8,000 extra, can't trust them. You don't really know where they go. Okay, so it just shows that you have a count here, which is the number of reads that are interesting. And then we can check, okay, out of those, how many are in the forward strand? 46,000. And on the reverse strand, also 46,000. You know, like these are two very close numbers to each other. That makes sense. Again, because every read has got one end that is on the forward, the other one that is on the reverse. So these two numbers have to be equal here. Okay? So one other thing that would be really nice would be to count how many reads are on the chromosome 2L, for instance, or on the chromosome X, or chromosome Y, or whatever that is. So this, unfortunately, we can't do easily. What we need to do is first to sort the read and to index them. So when we have an index, then we can actually count and see how many reads are in one particular region in the genome. So we can do this with SAM tools sort. So SAM tools sort map.sam, and really the curse of this SAM tool, something I really don't like about it, is that when you sort them, it doesn't produce a SAM file, it produces a BAM file. What's the difference between a BAM file? Nothing. It's the same thing, except that BAM is compressed. So there's just the compressed form of it. So whatever, minus O, sorted, mapped, BAM. Okay, it's super annoying the fact that SAM tools keep changing the format for the input and the output. I wished everything were either SAM or BAM, but it keeps changing. So after you sort, it's called BAM. Okay, well, you press enter. So we're not really supposed to do it. Sorting is an operation that takes compute, but you see it was just like 3 seconds, so that's fine. We're not going to be kicked out of the login node if we just do that. So now that this has been sorted, we can do SAM tools index sorted map.bam. I'll just press enter, and that's running super fast. When I do ls minus L, I can see that I have. So I'm going to zoom out so that people can see. SAM tool sort, SAM tool index. So so mapped SAM is here. You can see it. Sorted map BAM, and the SAM tool index has created sorted map BAM by. The by is the index here. So that is what we need to be able to directly count the reads that are in a particular region of the genome. So for those of you who missed it, SAM tool sort, but then you have to use the output in BAM file. So it means binary SAM. It's just that it's a compressed version of the format. That's what it is. And then SAM tool index, and you don't need to specify the file name. It's always called BAM by. Okay, so once this is done, then we can finally have a look at what we did. SAM tools view. If we look at the sorted file, so SAM tools view sorted, and then pipe less. You could see that the reads are sorted on the chromosome 2L. Their location here, as I'm scrolling down, you can see that this is sorted from left to right, basically from the beginning of the chromosome till the end of the chromosome. That's what SAM tool sort has done. Everything is on 2L, that's the first chromosome in Drosophila. It doesn't have chromosome 1. And you can see that they are sorted in increasing way here. Okay, I can do this, of course, with, let's say, minus Q20 to say, let's say, which are the ones that are above quality 20, and I'm seeing only the ones that are above quality 20. There's 2L, but there's 2R, the next chromosome. So how could I go to 2R? Either I can scroll down like this forever, but we don't even have time for me to go to 2R, or you can modify the call here, and you can say after sorted map SAM 2R. Now, it's okay to do this because we have indexed the file. It's not going to complain if I do that. So if I do this, now you can see that it starts on 2R because I'm only showing what's on 2R now. I've selected a window which is chromosome 2R. So that allows me to find where the reads are on chromosome 2R. And I'm selecting only the ones that are above quality 20. So I've got this quality sometimes, 24 still is a go. I'm just making a small comment about this one here. It's quite interesting. You can see that I'm selecting the read here for being on 2R. And what's in this column here, the equal, is where is the other end of the read. Remember, they are from the same molecule. So what do you think? One end is on 2R, and the other one is on another chromosome. Is that possible? Hell no, completely not. So something really wrong happened. Does it mean that BWA made a mistake? Maybe, but also maybe this DNA is not what we think it is. Okay, maybe this was actually something that has been ligated together for what reason during the preparation of the library. It's possible. You have artifacts like this. It doesn't mean that this is the end of the world or that BWA makes mistakes or that the Drosophila genome is wrong. Very often during the preparation of the libraries, you have some small artifacts that are created. So this would be, for example, a chimeric read that actually has two molecules in it. One half would be coming from 2R, the other one would be from 2L. Just, I'm speculating. We don't know for sure what happens there. Anyway, the point is that with this construct here, after indexing, you can do 2R, and that allows you to see only what's on chromosome 2R. And then, of course, you can count. You can say samtools view minus C for count, minus Q20 for keep only the reads that are high quality, and show me only the ones that are on chromosome 2R. And you can see that there are 16,000, on chromosome 2R. And if you compare to 2L, we see that there's approximately the same number that are here. Okay, so that's the way that we can find how many reads are coming from chromosome 2L, 2R, or 2L, or whatever we want. We can also, of course, ask other questions. What are the number of reads that are on the forward strand on chromosome 2L? Well, that's approximately half of them, etc., and that are high quality with quality 20. Okay, so you see the point. samtools view is the way that you can extract some information from the SAM format and the BAM format. And BAM is the same as the SAM format. It's otherwise really difficult, but just scrolling through this text, there's no information you can get. But if you use samtools, and in particular samtools view minus C, you'll be able to count the reads that have a certain property, like being above quality 20 or being on chromosome 2L. And I'll show you again the commands that were needed to sort an index. It was samtool sort here to sort the reads, and quite unfortunately the output is in the BAM format. And after this, it's samtools index and sorted map.bam. And you can see that, by the way, when you input a file either in BAM or SAM format, samtools is able to read it. Again, I really disagree with the decisions here. Calling samtools something that opens BAM, why not BAM tools? I don't know. Anyway, so that's the commands that you need. Okay, so we're done, we're on time. You've seen everything. With this, you will be able to do the quiz. So my recommendation is start with the quiz. It's going to open in 2 minutes. To answer the questions, you will need to connect to the cluster. Because there was a change in the cluster, some of the questions won't be possible. I'm going to change them now to make them possible, because I see now that this will not work with the new cluster organization. So I'm going to change them now, make sure that you see the new version of the questions in a few hours. Start with the quiz, because it's going to allow you to review today's class. I'm going to stop the recording soon, and then you can also view the recording again if you lost something. Working groups. Make groups that are working with 3, 4 people. That's a good number to work together. So working groups is going to be very advantageous. And then do the midterm. And remember, the midterm, you will have to do only the first two parts. I'm going to remove the third part. We have seen everything you will need to answer the midterm, but you will have to think. Some of the questions, I'm very sorry, but yeah, no, like it's not about knowing the commands, something like this. It's really about understanding biology and being able to think. So if you don't know the answer to the questions, it's normal. It's because you have to kind of go a little bit deeper and think what the answers could be. With that, I wish you good luck. Run home now to escape from the storm, and good luck with the quiz and the midterm.